Okay, so the last four lectures have been focusing on integer programming, where the point was to kind of try to understand or get a deeper understanding of some of the things we talked about earlier, like matching algorithms and stuff like that, by connecting it to linear programming. And the next few lectures are going to focus on trying to get a better understanding of something else from the lecture, which goes all the way back to week 1. So some of you might remember, so the minimum length or minimum weight spanning tree problem. Basically, so maybe I'll just review that. So recall the minimum length spanning tree problem. Right, so you're given a graph G and a length function which basically just assigns every edge to a real number. And your goal is to find a spanning tree. Oh, actually, so this is a connected graph. So G is connected, and you have some sort of length function, and your goal is to find a spanning tree of G of minimum length, where the length of a tree is just the sum of the lengths of the edges, right? And I understand probably some of you may have forgotten what a spanning tree is. So just to remind you, so a spanning tree of G is a graph, I'll call it T. So you have the same vertex set as G. You have a different edge set where E prime is a subset of E, so it's a subset, it's a subgraph, T is a subgraph of G, and T is connected, and also T has no cycles. So this is sort of review, but it's review from a long time ago, right? This, I think, was done in week 1. This is one of the lectures I wasn't actually here for, so, but yeah, so do people kind of remember this question, this spanning tree problem? Yeah, so, and you might remember that I think that 2 algorithms were presented for solving this problem, and one of them is really easy, right? Well, actually, both of them are quite easy, but probably the easier one is Kruskal's algorithm, which says, basically start with E prime being the empty set, and then kind of greedily add edges to E prime in such a way that you never make a cycle, and every time you pick the smallest length edge, right? So at each step, add an edge to E prime, which doesn't form a cycle, so it doesn't create a cycle, and subject to this has minimum length, right? So this is like, it's sort of weird that this works, right? This is sort of, if you wanted to do it in a kind of not very smart way, this is what you would do, right? You just take the smallest length edge, then I take another small length edge, I just make sure I don't make a cycle, right? And then eventually at the end, you'll end up with a connected graph, and you'll stop, right? So stop when B E prime is connected. Right, so if you, for example, if you had this situation, so this is your graph, and you have lengths, let's say 1, 2, 2, 3, 3, 4, right? So the algorithm just says, start by picking this edge because it has the smallest length. Now pick another small length edge, so either this one, so this is the smallest one left, or this one. They both have length 2. Turns out it doesn't even matter which one you pick. You just pick one arbitrarily. Now I try to pick the smallest length edge again. It has length 2, but this would form a cycle, so I don't pick it. And then I pick one of the smallest remaining ones, which is 3, and it doesn't matter which one I pick. And this just always works. Just sort of weird, right? So basically we're going to be interested in, why does this work? So why does this greedy approach work? And the answer, as it turns out, is going to be because the structure, the underlying structure of this problem is a matroid, okay, which I'll define in a minute. But the answer is, let's see how I phrased it. Yeah, so the collection of, I'll just say, spanning acyclic graphs, acyclic subgraphs, forms a matroid. And that's the sort of deeper reason why this greedy approach works. Okay? And so now I'll define what a matroid means, and then I'll actually prove that this sort of structure actually does give you a matroid. Any questions about any of this? Yeah, and tomorrow we'll actually prove that, yeah, like in a very strong sense, this is really like the answer, in the sense that, like, whenever you have some sort of problem where the greedy approach always works, then actually you're dealing with a problem that involves a matroid. And it's a sort of, it's an if and only if. Okay. So now let me define them. So let X be a finite set, and let I, so it's going to be a kind of curly I. So let I be a collection of subsets of X. Okay, so now the pair, so X, I is a matroid if the following things hold. So first of all, so this is kind of a trivial condition. So the empty set is in I. This is just sort of to make sure that I is not empty, but otherwise this is almost never very important, this first one. Secondly, you want that if Y is in I and Z is a subset of Y, then Z is in I. So it's closed under taking subsets. And the third thing, so this is usually the crucial and kind of most difficult property to satisfy. So if Y and Z are both in I, and Y is smaller than Z, then there exists X, which is in Z but not in Y, such that Y union X is in I. So I understand that this looks super kind of abstract, right? I mean, it's just kind of a bunch of kind of set notation. Is there any questions about, is everything clear what I'm trying to say here? Okay. Yeah, so this all looks kind of abstract, but actually these are, this notion of, so this, it's a very general notion of a this notion of matroids. It actually encompasses a lot of things that you kind of know about. So things like trees, but also things like, well, some things from linear algebra, like sets of independent or dependent vectors. which I'll explain in a few minutes. Okay, so just some terminology. So given a matroid xi, a subset of X is said to be independent if Y is an I, and dependent if Y is not an I. And this just comes from, I mean, the terminology here, it just comes from, I mean, basically linear algebra, right? And we'll see that when we talk about, you know, these kind of linear algebra types of matroids, this is going to really just correspond to linear independence and linear dependence, which is, yeah, things hopefully you're used to. But generally in a matroid, yeah, a set is independent if it's in I, it's dependent otherwise. Okay. Yes, let's get into some examples. So the first example is going to try to connect to this idea of spanning trees. So these are called graphic matroids. They're called graphic matroids because they come from graphs. That's the only reason. Okay, so let G be a graph, and let I be the collection of all subsets of the edge set, such that, so the graph where you take all the vertices of G and you take that specific subset of the edges has no cycles. So I claim, so here now this set X, so from the definition of a matroid, is going to be E. So it's the edge set of the graph. And I claim that this pair is a matroid. Any questions about the definition of this? Okay, so to show it's a matroid, we just have to go through these three properties one by one and just tick them off, right? Just check that they're satisfied. So, okay, the first one is almost always trivial, right? So the fact that if I take a set of vertices and I put no edges at all, right? This obviously gives you a graph that doesn't have a cycle because it doesn't even have any edges. So empty set is in here trivially because having a graph with no edges implies you have no cycles. And usually, you know, this second condition is also pretty easy. It turns out to be pretty easy in this case. So here we're saying, so suppose, well, so here if you know that, say, VE prime has no cycles, and let's say E double prime is a subset of E prime, right? So then if I look at the graph VE double prime, that's basically the same graph except maybe I've removed some edges, and removing edges can't cause you to have a cycle, right? If I take a graph and it doesn't have any cycles and I remove some edges, it still doesn't have any cycles. So then, okay, so this kind of, so this sorts the first condition and that finishes the second. And as usual, the third condition is the more tricky one. So this is where we're going to have to actually understand something about graphs with no cycles. Right, so let's prove that, let's show this third condition is satisfied for this particular matroid, or this particular pair. So, yeah, so we're going to do this, we're going to use the following lemma. Okay, so it just says that if you have a graph with no cycles then actually you can figure out it's quite easy to figure out exactly how many connected components it has. So then H has exactly number of vertices minus number of edges connected components. Something similar to this might have been proved in week one when you're doing spanning trees, but maybe not exactly the same. Okay. So we're going to go by induction on the number of edges, where we're going to start our induction at 0, right? So the case when the number of edges is 0 is trivial, because when you have no edges at all, then every vertex forms their own connected component. So you have exactly size of V components, right? Because this is just, yeah. So in this number of edges is 0, your graph is just a bunch of isolated vertices. Okay, so now for when you have an edge, at least one edge, we just let E be any edge and consider the graph H prime, which is the same as H, except we remove that edge, right? So, yeah, and so by induction, H has size of V minus size of E minus E, little e, which is V minus E plus 1 components, connected components, right? Because this is just what the induction hypothesis says. And, okay, so let's look at the endpoints of this edge. And I claim that in H prime, these guys have to be in different components. So U and V are in different components of H prime. Otherwise, basically, if they were in the same component, there'd be a path between them. So find a UV path, so path from U to V in H prime, and add the edge E to form a cycle in H. Which would be a contradiction, right? So the picture is like this. So if I look at H prime, it has some components, right? And if U and V happened to be in the same component, I would look at the path between them in that component, plus I recall that this edge E from U to V was in the original graph H, and I would get a cycle, right? Just like, and so therefore, so this picture can't happen. So therefore, what the picture looks like is that you have U and V in different components, right? And now the point is, when I put this edge back, it will cause those were separate components of H prime, and now they'll become the same component of H, because they're all now connected together via this edge, and now the number of components drop by exactly 1. So adding E drops the number of components by 1, because it just merges the component containing U. And they become the same component. And so H has 1 fewer component than H prime, which is V minus E components. Okay, so the point of that was we want to now establish this third condition of a matroid using this lemma. So maybe I'll leave this definition because it's quite a hard one to remember, I think, and we're going to need it again. Yeah, so finally, so let's prove that this thing is actually a matroid. So we have to establish the third condition. Proof of the third condition. So so let's say E prime and E double prime be an I, where the size of E prime is less than the size of E double prime. So these are both sets of edges which form graphs without cycles, and this one is bigger than that one. Right? That's the setup from, it's here, condition 3. And okay, so by the lemma, we know that V E prime has V minus E prime components, and V E double prime has V minus E double prime, which is less than V minus E prime components, right? Because this is bigger than this, so therefore this is smaller than this. And this means that, so therefore there must exist an edge E in E prime, or E double prime, which joins vertices in different components of VE prime. So this is just by the pigeonhole principle, okay? And then it's not hard to check that if I look at VE prime union that edge, that has no cycles. Okay, so the picture is basically like this, right? So if I look at, this is my graph VE prime, it has a bunch of components, right? And I know that, okay, so here what I'm saying, so I know that if you look at the edge set E prime, E double prime, it has fewer components. Therefore, so from that, all I'm going to use is the fact that if I look at, if I look at the graph VE double prime, it can't have the same components as this in terms of it can't join up just the same vertices as this one does because it has fewer components. So therefore, somewhere there has to be some kind of edge that goes from one component to the other, and that's the edge that I pick. So this is the edge E. And you can see that if I just add one edge between these two components, it won't make a cycle because the cycle would have to come back. Okay, so this is actually a matroid. Any questions about that? Okay, let's do another example to kind of show you that matroids apply much more generally than just to graph theory problems. So this is something called a linear matroid, and the reason is just because it comes from some sort of linear algebra. Okay, so let A be an m by n matrix. X is the set of all column vectors of A. So so it's the set of all. So this has so this is m rows n columns. So just to kind of just in parentheses. So the size of X is n. It's the column vectors of A, and let I be the set of all subsets of X, such that the vectors in Y are linearly independent. And this sort of, okay, the fact that this is, so, okay, I claim now that this is a matroid. Okay, and so this particular example kind of explains where this notion of, or this idea, this definition of calling like sets in here independent and sets not in there dependent comes from, because, I mean, in this case, these are literally the linearly independent sets. Also, this sort of explains where the word matroid comes from, because, yeah, in some sense, so here we have a matrix. In some sense, a matroid is a weird generalization of a matrix, right? So it's not a matrix necessarily, but it's a matroid, right? Okay. Okay, so I claim that this is a matroid. So again, two of the conditions are going to be easy. So, well, okay, it sort of depends on, it's kind of annoying how, it depends sort of how you define linear independence and dependence, but let's say that an empty set of vectors is linearly independent, right? Because there does not exist, yeah, anyway, it doesn't matter. Let's just, yeah, so kind of, here we're kind of assuming an empty set of vectors is linearly independent, okay? And the second condition is easy. So remember, the second condition says if you have something that's independent and you take a subset, then it has to be independent. And this is just because, yeah, so if y is linearly independent and you remove some vectors from it, so z is a subset of y, then z is linearly independent as well, because you can't create dependencies by taking a subset. And so as usual, the tricky thing is to prove the third condition. Okay, so so just going by the definition, so let y and z be independent such that y is smaller than z, right? And we want to prove that there's some element of z that I can move over to y so that it stays, so that y stays independent. Okay. So we want some x, which is in z, not y, such that y union x is independent, which means in this case linearly independent. So if it doesn't exist, then what does that mean? So then if I take anything in this set, it's contained in the span of the elements of y. So then so remember, this x is a vector, right? It's a column vector. Or let me say, so then every such x satisfies that x is in the span of the vectors y in y, right? Because if it's not linearly independent of them, then it's in their span, right? And also, obviously, every vector in z intersect y is in the span of this, or yeah, why would I write it like this? I can just write span of y, right? So here I just mean the span of the vectors in y. Because, okay, I mean, because z is in here, so z is actually in y, so yeah. But then what this means is, so everything here is in the span of y, everything here is in the span of y, so therefore z is in the span of y, right? But that's impossible because so that's a contradiction, because the size of z is bigger than y, and you can't have more than, so you can't have, and so you can't have z linearly independent vectors in a space with dimension less than z. So let's say a space of dimension y, right? So the span of y, since y are linearly independent, this has dimension exactly the cardinality of y, but somehow we found more than y independent vectors in there, but by linear algebra that can't happen, right? This is you can't find more than the dimension number of linearly independent vectors. Is that clear? Okay, so therefore there must exist some x there that can be moved over to y. Okay. Okay, so I'm just going to end now with a lemma and a couple of more definitions, which I'll probably repeat tomorrow. Well, I won't repeat the proof of the lemma, but I might repeat some definitions, because I'm sure that all of this is kind of new to you. So here's well, actually, first I need a definition. So given a matroid xi and a subset of x, so a subset of subset B of y is called a basis for y. So it's a basis for y if it's independent. So all of these definitions, you should really think of what's the analogous definition in linear algebra, right? So, okay, so it's a basis if it's independent, just like in linear algebra. So basis has to be linearly independent. And if I try to make it bigger, so if I take B union y, this is not an independent set for any y which is in y, little y which is in capital Y minus B. It's a basis if it's a basis for y if it's a subset of y which is independent and you can't increase it to a bigger independent set within y. So here's a lemma. So B1 and B2 are bases, so plural of basis is bases for y, then they have to have the same size, which is also something familiar from linear algebra. But here we're obviously dealing with much more generality because we're talking about, this is something that holds for any matroid. Okay, I'll leave this. And this just comes from this third axiom from the definition of matroids. This is actually pretty easy to prove. So here I'm proving this lemma right there. Okay, so if not, then, of course, without loss of generality, I can assume that B1 is less than B2, smaller than B2. But now I just apply this axiom. So B1 and B2 are both in I, and one is bigger than the other. So by the third axiom, or the third condition, we know that there exists some x in B2 such that B1 union x is independent. But that's a contradiction because so this x is actually in B2 minus B1, right? That's what this axiom gives us, or this condition. And we know that, remember, just by definition, B2 is a subset of y. So this new element x that we introduced is in y, and so B1 union x is a subset of y. But yeah, or actually I didn't really need to prove that. Anyway, this doesn't matter. So this contradicts the fact that B1 is a basis for y, right? Because we found a point which is in y, which is not in B1, such that when you add it, it stays independent. Okay. So this concept that all bases have the same size allows you to define a sort of something that's quite similar to like the dimension of a vector space or the rank of a matrix. And fittingly, it's called rank. So again, we assume we have a matroid xi. So the rank of a set, of a set y contained in x is defined to be the size of B, where B is a basis for y. And by this lemma, we don't need to say which basis because they all have the same size, right? So let me just finish with with a couple basic definitions. So so here we've defined what it means for a set to be a basis for y. Sometimes I'll say basis without specifying the set y, and in that case, it just means it's a basis for x. So a set is simply called a basis if it is a basis for x, meaning like you just take that definition, you apply it to the case y equals x, and the rank of a matroid, right? If I want to talk about the rank of the whole matroid, that's just defined to be the rank of the set x itself in the matroid. So it's defined to be the rank of x in the matroid, which is the size of the biggest basis. So, or size of a basis. And we know all bases have the same size. Okay. Any questions about these definitions? Like I said, I'll probably repeat them tomorrow. Okay.